Hey, fellow science teachers. Did you know about the pervasive misconceptions concerning the thermodynamic role of ATP in cellular processes? Well, I didn't until I grappled with it myself while going over cellular respiration in AP biology after completing the thermodynamics unit in AP chemistry. I did some online research and found several peer-reviewed studies that confirm these misconceptions exist and not just in my head. For your reference, these studies are all linked in the description below. One study even stated, students grapple with the apparent contradiction between the energy released when the phosphate bond in ATP is broken and the idea that an energy input is required to break a bond. Khan Academy, an amazing science resource, has been a great help to many of my science students. I'm showing you here a very simple image of ATP hydrolysis. The words requires energy are very helpful by underscoring that it takes energy to attach the phosphate group of ADP to obtain ATP. I get it. It's tempting to state that the charged battery implies that ATP has a high energy bond. But in fact, it is because of the weak bond between the terminal phosphate and the rest of the molecule that renders it more likely to form a stronger bond with another atom. This part is emphasized in the diagram by the term releases energy when the phosphate group is removed. Let's go into this process in more detail while keeping the big idea in mind. Net energy is released when weak bonds are broken, which requires energy, and strong bonds are formed, which releases energy. Then we'll come back to the Khan Academy drawing with a slight twist that may resolve the misconception. Maybe. I will now take you through some animations that I constructed that may help in resolving this ATP misconception. Check out the link above, as well as the description below, to obtain access to these animations so you can try it out with your science students. Leave me a comment to share your experience with this concept. All right, so ATP is composed of a nitrogenous base called adenine, a 5-carbon sugar called ribose, together referred to as adenosine. And these two components are attached to 3 phosphate groups, hence the name adenosine triphosphate. In the presence of water, there are 2 relatively weak bonds that can be broken through the input of a little bit of thermal or kinetic energy, as is indicated by the 2 smaller sized blowtorches. When these bonds are broken, ATP is now turned into ADP, adenosine diphosphate. What happened to the remaining? Well, that basically resulted in 2 broken bonds, which can now reform inorganic phosphate, a much stronger bond that results in the release of more energy, as indicated by a larger blowtorch. So now we've turned ATP into ADP and inorganic phosphate. Weaker bonds were broken, stronger bonds were formed, hence the release of energy. Another way of showing this is with these thermal and potential energy bar diagrams. So we're looking again at the ATP molecule, adenosine triphosphate, with the 2 smaller blowtorches about to break the existing relatively weak bonds. That is shown here by the reactants, the bonded atoms before the reaction, with a relatively high bar for the potential energy and another relatively high bar for thermal energy. Now we're going to break those bonds, and that means we are now in a transition state where the bonds have been broken. That means there's a lot more potential energy. Imagine as if you were biking up the hill. You're now at the top of the hill. The only way is back down, which is a very favorable direction. So there's a lot of potential energy, and we can now turn that into a lot of movement or heat release when new, stronger bonds are formed. And that's exactly what's going to happen now. So the stronger bond between the last phosphate group and the hydroxyl component of water are going to form that stronger bond. That is indicated by a much lower potential energy bar. You see that drop in the green bar. And because new bonds are formed, you're seeing a high increase in the thermal energy bar because of these new bonds that are stronger forming, therefore this concomitant energy release. So to summarize that again, we had an input of a small amount of energy to break the existing bond, an output of a larger amount of energy to form the new bonds. We had a starting relatively weak bonds with relatively higher potential energy. We ended with strong bonds that have a relatively low amount of potential energy, which is what nature favors. If you then connect the reactants to the products, this looks actually as an exergonic or exothermic energy diagram. The starting potential energy of the reactants, and then the ending potential energy of the products, which is lower, and the concomitant energy release. We're going to use that diagram to upgrade the Khan Academy diagram. Let's get to it. So we are now back at our Khan Academy diagram, where we're looking at the words requires energy. If we add to this diagram the actual energy curve that shows you that we're starting low and we're ending high, to really emphasize that input in energy when we're forming the ATP molecule. And therefore we get that so-called charged battery, not because we have a high energy bond, but we've now formed weaker bonds that can then form new bonds that are stronger with concomitant release of energy. And a result, you now have a dead battery. And again, you see that second energy curve in red, where you're now ending lower on the potential energy diagram. I hope you find these animations helpful, either for you and hopefully also for your students. Try them out on your biology and chemistry students, as well as your AP science students, if you have them. Can't wait for your feedback. Bedankt voor het kijken en tot ziens. Thank you for watching and see you in the next video.